Please welcome to the stage SC24 General Chair, Philip Roth.
Good evening, everyone. I'm going to tell you more about our conference tomorrow, but tonight it's my honor and my pleasure to introduce Miles O'Brien, who's going to moderate the panel that you're about to see. Miles O'Brien is an acclaimed independent journalist specializing in science, technology, and aerospace. He serves as the science correspondent for PBS NewsHour and contributes to Nova and Frontline as a producer, director, writer, and correspondent. In April 2025, he will debut as the executive producer and host of Resolve to Solve, a new science series on Arizona Public Television. Throughout his 4-decade career, O'Brien has garnered awards for his insightful reporting. He spent nearly 17 years with CNN, where he focused on science and aerospace, and arranged an unprecedented agreement with NASA to cover a space shuttle mission firsthand. Please welcome Miles O'Brien. It's okay.
Everyone who outlast the applause, good to see you. It's good to be here. HPC Creates, Atlanta, Georgia. I lived here for 13 years, right across the way there at the former CNN Center. I hope you're enjoying Atlanta so far. We have an extraordinary plenary panel here. Our theme is HPC Creates, and it can't be more fitting for this panel. We've got experts who create smarter airplanes, blockbuster movies. They look at exploding stars. We have somebody who's familiar with quantum realities. It's kind of the ultimate creator toolkit. But instead of paintbrushes, they're using petaflops and qubits. So we have a lot to talk about and a lot to stimulate your brain as you begin this fabulous conference, as you think about how HPC can create new things for the world and make the world a better place. And I'm told there's an absolute record turnout here. 17,000 people are here, so give yourself a round of applause for being here together. Who knows what great ideas and what creative things will come out of this. Meetings are back, I guess, for sure. All right, let's get the panelists out here. Our first guest is the Chair of Aeronautics and Astronautics at Stanford University. He's a man who focuses a lot on the future of flight, while I spend most of my time on kayak trying to find cheap flights. He is a pioneer in computational simulation, and he fancies himself as finding some way to come up with a Jarvis, as in Iron Man Jarvis. When he's not solving engineering problems, he's dreaming about ways to make airplanes better and faster and greener. Please welcome Juan Alonso. See you, Juan. All right, our next guest is a visual effects wizard. This is hometown for him, too. He's worked on movies, everything from La La Land to Stranger Things. He co-founded a company called Crafty Apes, where he works on Hollywood dreams and turning them into great, spectacular, jaw-dropping visual spectacles. And now he has a company called Luma Logic, which is bringing cutting-edge AI into the filmmaking industry holistically, the whole process of making a film. So if you've ever wondered about what makes those explosions look good and what makes things look cooler or scarier or grosser on your film, this is the man who does it. Please welcome Chris Ledoux. Good to have you here, Chris. So we're going to go from fake explosions to real explosions now. Our next guest is at the Oak Ridge Leadership Computing Facility. He is the director of science there. He's an astrophysicist who is trying to unravel the mysteries of exploding stars and what the contents of exploding stars have to do with us. So he's sort of like CSI supernova. On top of that, just kind of as a side hustle, he is a Jeopardy champion. He won Jeopardy and paid off his mortgage. Please welcome Bronson Messer. Good to see you. And finally, let's get to really, really small now. A quantum computing powerhouse from Fermilab. She's working on stuff that's so advanced, I will tell you, I tried to do a story for the PBS NewsHour on quantum computing, and I crashed and burned miserably. When we got into the idea of entanglement, we lost the entire editorial team there. So, but I know this group gets it. So how to make quantum computers talk to classical computers is a big focus of what she's working on. It's kind of like, I suppose, getting cats and dogs dead and alive to play together somehow. Please welcome Silvia Zorzetti. Good to see you. All right, let's get right to it. We're going to start with Juan, since you were the first to come out. Juan, tell me, you were involved in applying HPC to simulations and to engineering problems. First of all, what's the vanguard right now? What is the newest stuff you're working on? And I know you're focused, a lot on aviation and coming up with simulations and so forth in the process of developing aircraft. I'm curious what has you charged up right now.
Well, as you will say, I'm an engineer, and I think, as many engineers here in the audience, engineers solve problems. In my particular case in aerospace, I'm interested in solving problems that involve the physical world. So for that, I rely heavily on simulation. And it's truly amazing that we've gone over the last 25 years from being able to do one simulation every 25 hours or so, to being able to do 10,000 simulations in less than a day today. So translating all that HPC capability into what excites me today, I'm an airplane person too. I think the main challenge that we have in aerospace engineering from the aero side is the sustainability of the commercial air transportation enterprise. How are we going to get to net zero emissions in all of the aircraft that you flew in here today or yesterday or the day before, and to do so in a manner that continues to allow the growth of commercial air transportation and at the same time enables us to do so with complete sustainability. So that has me very, very excited. And the HPC elements that are going to facilitate that have me very excited.
So tell me about your Jarvis desires. What are you after?
So I said I'm an engineer, but I also feel that I'm a designer. I'm an aircraft designer. So my main interest is in trying to explore very vast design spaces. Human beings are actually very good at this, at pruning sort of the space of all possible options, let's say for an environmentally sustainable aircraft and its propulsion system. I think engineers have spent way too much time in simulation doing IT tasks. And what we need is effectively a Jarvis-like analogy. Tony Stark had it right. The ability to compute almost instantaneously, so a human being can actually come up with ideas of what the next generation aircraft might look like. And a Jarvis-like, if you don't know what Jarvis is, it's the AI from Tony Stark. A Jarvis-like system can actually give instant feedback as to the suitability, the performance, the reliability, and the safety of these types of vehicles. So I'm very excited about HPC becoming almost real time, and having AI sort of help us decide what are the true and most impactful aircraft and propulsion system configurations we may have in the future.
So we've been designing airplanes, without sketching out blueprints for a long time. Right. The natural evolution here is you could get to the point where you go through at least some part of the certification process. Right. Without actually building things. Is that even practical or imaginable?
Oh, 100%. We call this certification by analysis. And you can imagine when you design a new aircraft from scratch, particularly one that is very sustainable and leaps and bounds beyond in technology from what we have today, you have the entire process of design, of putting together the initial systems, and then eventually at the tail end of a 10-year process, you have to certify that the aircraft is safe, so you and I and anybody here is comfortable sitting on that airplane going from one place to another when the technology may be quite different than the technology that we've used in the past. So right now, for a new aircraft, we spend between 1.5 and 2 years, and although the big companies won't tell you this, upwards of $1.5 to $2 billion to simply go through a process of building physical prototypes that we flight test to demonstrate the safety of an aircraft. Why can we not do that, or at least large portions of it, based on simulation? We call this certification by analysis, and the basic idea is to understand the very risky maneuvers that can be appropriately simulated with significant degree of certainty, so you can convince a regulator, so you can actually bypass some elements of the flight testing that actually take so much time and cost so much money.
Well, so there still has to be a role at some point for old-fashioned wind tunnels, or not?
Well, I'll tell you, in 1972, 3 very smart gentlemen, so Dean Chapman, Hans Mark, and John Purtle, put together a paper that said that by the end of the 80s, we would take all the wind tunnels out and we'll be able to replace them by physical simulation. So they effectively missed that prediction by a good 40 plus years.
We were supposed to be on Mars too, so anyway.
We also were supposed to have a lot of other things. Well, but with that said, over those last 40 years, our ability to simulate has grown exponentially. The fidelity of the algorithms and the methods that we use has also increased tremendously. And the combination of the two is allowing us for certain parts of the operating envelope of an aircraft to do everything via simulation. There's still some areas where turbulence and some other things are not well resolved enough by current models, and we have to rely on physical experimentation. But the amount of physical experimentation we're going to be doing in the future compared to simulation is going to be shrinking, and it's going to be confined to those areas where the simulation is still not good enough to replace the physical worlds.
So would you have any misgivings getting on an aircraft designed and certificated this way?
Not if you can convince the regulator what the FAA calls the equivalent means of compliance. So you either show it to me by flying an airplane and performing a maneuver, or you convince me, the regulator, that the information you're getting from simulation is as accurate or has as few uncertainties as the flight test itself. So what that's going to mean is that instead of running one simulation at a time, we're going to be running ensembles of simulations. We're going to be quantifying errors and uncertainties, understanding the safety margins that these vehicles actually have, and then and only then, I would actually be happy to get into one of those airplanes that has not been fully tested with a prototype.
All right. Maybe we shouldn't tell the flying public the full story, right? You never know when it's the guy's first landing, right?
Transparency is the best policy.
Right, transparency is good. Yeah. All right, Chris, let's move it to you for a second. Let's talk about the entertainment business. First of all, a lot of your work has been perhaps a little more subtle than some of the typical Marvel stuff you can imagine. It's almost like augmented reality, sort of enhancing scenes that are already shot. I'm curious about that approach to special effects and graphics. In a way, is that a harder challenge because you're trying to be as real as the real world and not create these separate environments?
Yeah, I mean, there's something, if you take an element that we know doesn't exist, if it's, say, a dragon or something, cognitively, when you watch it, something happens to your expectation, versus if you're, say it's Juan driving in a car and it's a green screen. Well, we have a certain preset for what we know that needs to look like, and when that's violated, it really bothers us, and that's when you see a lot of people react negatively to facial. We're really, our brains are very tuned into facial identification. The moment you start screwing with that just a little bit, people know there's something wrong. And so the subtle effects are not if we do our job correctly, no one knows we're there. And that's the best time that's the best job we can do there. But, there's times when it's, a planet explodes and, nobody filmed that. in theory.
So
Juan might have filmed it, like the rest of you.
yeah, so our next guy probably has that, but you have a little more creative license if it's completely spun from whole cloth.
Then it's all left up to interpretation. Although it is surprising how many directors will disagree on what reality looks like, because when you actually show them, that's the best trick you do is show them a real shot, and they start making notes and complaining, and you're like, no, that's actually practical. And so that's it's mainly a mental game there.
So what's most important in your world? Just sheer computing horsepower, or is it the classic quality of data? The garbage in, garbage out problem.
I mean, traditionally it was raw computing power, but now that in the last couple of years, as we've delved heavily into training models and things like that, it's actually it's more of a data and an architecture problem, and it's actually defining the frameworks for things. And so similar to Juan, actually, we're obsessed with simulation. And so if a lot of our biggest, most complex things were actual simulations, fire, smoke, wind, things like that. And the calculations we'd have to do sometimes would take the renders for like, say, 2012 or day after tomorrow would take weeks sometimes. And it doesn't really need to be that way. It turns out you can shortcut a whole lot of things to get there and arrive at the same destination. And it's just all about controllability. And we have extremely fine control right now over most things. And as we delve more into the AI, that's the part we're trying to get back, is there's a lot of control that gets lost. You kind of have to hit a wider target, and filmmakers don't usually like that. So,
well, tell me about how what you do is integrated into the creative process. Are you guys there from the beginning, from the original idea all the way through, or do they come in at the tail end and say, okay, put some special effects on here to do this, or is it some combination?
Right, if it's done properly, it's the first way. It's the second way a lot of times. It just depends on what they're doing. I think we're going to become more and more. A lot of what we're doing now is looking at it's funny how similar it is to what you were talking about, is we're actually simulating out how audiences will react to different emotional moves in the story. And then also working on things where we set up an environment and have characters with goals and then simulate it out to see what the characters would do, and then you simply observe it. And that could become a script. So if you say, Miles, if you say, I was going to be the quarterback of the Jets or something like that, here's the simulation of what would have happened. And that's a really interesting idea, because the more you define these environments to a higher fidelity, you can get much finer details. So I think movies are evolving very rapidly now in terms of what's going to be coming out in the future.
Well, movies have always been, focus grouped to death. This takes it to a whole different level, doesn't it?
Well, I think it has to, because there's been so much content now, and the industry is financially devastated. And so if you look at the numbers on who's watching, like Netflix is not the number one, it's actually YouTube, and it's highly decentralized. And so as it becomes more niche, the experimentation can go up quite a bit, actually. And so that's when you're going to start to see a whole bunch of different experiences, especially as augmented reality and glasses become more prevalent. You're going to see a lot of interesting stuff happen. So it won't be as, movies traditionally have been very passive, director, making thing, and then viewer. And I think we're about to see a lot more interactivity.
Well, this is going to really be a sea change for storytelling, and it really creates the possibility of truly personalized entertainment. What's that could be like? I mean, if we don't even have a show to share with anybody. What are you watching on Netflix? Well, I'm watching the show that I imagined.
I think it's going to open it up a lot more. I mean, traditionally in Hollywood, the people who were telling the stories, if you were to look at like what's the number one correlating factor to who got there, and I wouldn't say it was the best storyteller. I think it's actually like most things, it's socioeconomic. Like whoever had the most money was most likely to become the most successful director because they had more time to play with it. So I think it actually opens it up a lot. It'll open up a lot of noise too. And so that'll give rise to a curation class in certain niches. I'm curious to see, will the death of the blockbuster, happen to a degree, and that sort of glue, that cultural glue, like, he mentioned Jarvis, but I actually made a bunch of the HUDs for Iron Man on the movie. So it's like at one point, so it's like that kind of glue, though, like if we say Jurassic, I'm 45, if I say Jurassic Park, every single person knows what I'm talking about. In 30 years, is that going to happen for my children? Where there'll be a cultural event when I'm like, do you remember when the Tyson fight got all screwed up and he was 70 years old? Like, that's now the cultural event. So I'm curious, will that glue still be there?
Well, we'll always have that or the Super Bowl or whatever, but what happens to our society when we don't have those shared blockbuster cultural events.
In one sense, it could be bad. In another sense, it might give voice to a lot of people that have not traditionally been able to have their voice heard. You know, and you really look at a lot of these amazing stories, like if you look at, say, This American Life or something like that, you know, and it's a great data set, by the way. They have all 700 episodes. You can train a model. But you look at that, and there's a lot of success there. And so I think amidst all the noise and things, if you look at a lot of the complaints about, say, AI-generated video, and they're well-founded. It's that it's just a bunch of stock footage without meaning, context, and soul behind it, and human connection. It's somewhat meaningless. And you could say that about any footage. Context is everything. And so I think they're actually, if the platforms are there, people will find audiences because you're seeing just incredibly niche material, you know, come out now that people appeal to us.
Yeah, you were talking with me before about this ontological shock that people have as they react to AI and VFX. What do you mean by that?
Well, I think and I was at a Directors Guild event a couple days ago, and it's shocking how little people know about actually what's out there. And I've had the gift of time the last couple of years, so I live on GitHub 24 hours a day, and I'm like, look at that, look at that, look at that. And so, but most people aren't even aware. You know, I got guys coming, you know, have you heard of this ChatGPT thing? I'm like, Jesus Christ. And like, you know, so they don't realize how much you can vectorize things, measure it, and then deliver an output. And that it is just not where people are living. So I've never, in my lifetime, never seen anything move so fast that people aren't even aware of what's already out there before it's like, you know, it looks like magic to them. And so as it accelerates, I think initially there's a very negative reaction because any kind of change like that, people react negatively to it. And I think there was some French sociologist would talk about this 100 years ago, called it anomie. It's a weird sort of cognitive dissonance that happens. And so it's already hitting, and you know, in the VFX world, it's going to be devastated, quite frankly, because of the acceleration. And it's going to have to rebuild, and I think it'll rebuild better. But right now, there's a lot of anger and fear because it's so fast. But
the moral of your story is that you still think humans want to connect with humans and in a meaningful way. Those are the stories that work.
The shock is that your internal narrative about how the world's supposed to work is all of a sudden violated. Like you've seen something that's not supposed to be possible happen, and you're like, wait a second. And so you have to reset your view on the world. Now, eventually, you adapt because we're good at that. But it initially, you see the reaction in my industry. I mean, sorry, I'm ADHD, so I always lose my train of thought. Like, thinking about cats right now. I totally forgot what I was going to say.
Let's talk about supernovas anyway. So, all right, Branson, you are literally trying to trace the elements from their origins. So the iron we experience, the gold that we have on our wrist, whatever, tracing it back to the supernova from whence it came. Easy problem, right? Simple. No need for a lot of computing horsepower there. Compare that to other complex, computationally heavy problems that we face, like climate models, et cetera. Where does that come in?
I have a privileged seat being the director of science for the world's largest computing center. So I get to see a lot of simulation types distributed throughout. And there's nothing as multi-physics, as multi-scale, and as highly computationally intensive as how a star dies. How does a star form those things that make us us? As you alluded to, all the iron in our blood, all the gold around our necks. Everything that sort of makes our reality is formed in a star and then is spit out into interstellar space by the explosion of a dying star. This sort of connection with our roots, in a very real sense, is sort of what drives me. Secondarily, what drives me is how hard the problem is. I freely admit that when I was a grad student in physics and I was sort of looking for a field, I picked the hardest problem I could find, mostly because I also loved computers, and it also seemed like the right thing to do if I wanted to use computers to learn to bend them to my will to be able to solve this problem. So it is a problem that has vexed us for way more than half a century. We've sort of known the pieces that we have to put in to understand what happens when a supernova explodes, but we've never quite had enough computing power to be able to accomplish that. But real progress has been made, as Juan was alluding to earlier, concrete progress has been made over the last 2 decades that really allows us to have a completely different view of what we can do, what we can understand, and the kinds of models we can build and then learn from.
So try to give us a sense of the complexity of determining where the iron in my blood came from.
So, you know, a star is, in some sense, a fairly simple object, right? I mean, to zeroth order, it's a spherical cow. They're pretty much just big round things, right? But they're these huge things that are being held up against their own self-gravity by nuclear fusion, which I think we've all heard of. You know, I often ask school kids, what makes the sun shine? And there'll be 1 or 2 precocious kids that'll say, hey, it's fusion. You're absolutely right. A big star, something that's, say, 10 times the size of our own sun, not only can it take the hydrogen that it's made up of and fuse that into helium, it can then take the helium, fuse that into carbon, the carbon into silicon, the silicon into iron, and then the star is kind of screwed. Because the problem is, iron sits above, right at the tip of what's called the curve of nuclear binding energy. You can't take 2 iron nuclei, slam them together, and get any energy out. And so what happens to the poor star is it starts to grow this core made of iron that just inexorably grows larger and larger and larger. And it turns out that it's not being held up by fusion anymore. It's being held up by a much more mysterious force, but anybody who's taken high school chemistry sort of has a feel for it. If you took high school chemistry, and I start to mention this and you get flashbacks, I'm sorry, but you know when you had to fill in electrons and spin up, spin down, spin up, spin down, that's because electrons are this special kind of particle that have a 0-point energy even if they're at absolute zero, because they can't all occupy the same state, the same quantum state, which I'm sure Sylvia will tell us about in a second. That's all that's holding up the core of that star. So I've already moved from doing compressible hydrodynamics and other kinds of cool things that, for example, Juan would do in a simulation, to doing subatomic physics. And oh, by the way, there's a limit to how much I can hold up. It's called the Chandrasekhar mass. It's about 1.4 times the mass of the sun. When that happens, the core collapses, and in literally a half second, it rebounds, forms a shock wave that will eventually rip the star apart and spit it out in interstellar space. There's a lot of physics that I just elided in that big clap, and that's been the project for the last half century or so to figure exactly what happens.
All right, so unpack the clap for us. How on earth do you ground truth a simulation like this, right? I mean, when you're doing a climate or weather model, there are ways to check your work.
Yeah.
This is a little bit harder, isn't it? There aren't too many weather stations out of the supernova.
The lucky thing is there's so much physics, there's so many observables. And that's the other thing that's gone along with the inexorable march of computing power. We have very good detectors now. We have terrific gamma-ray satellites that can tell me what the isotopic composition of exploding stars actually looks like. I also, for example, have access to data from detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory. You shake that much stuff, you shake and collapse and ring 1.5 times the size of the sun, it leaves ripples in space-time, and I can actually see that with detectors like LIGO. In addition, core collapse supernovae in particular produce these kind of very ghostly particles called neutrinos. If you've ever heard of neutrinos, you've probably heard that they're the apotheosis of ghostly. If you hold your hand out, there's 70 trillion neutrinos from the sun passing through your hand every second. They'll never interact with you, they'll never interact with the Earth, they'll go straight through. That iron core that collapses, though, it's so dense, so unimaginably dense, that a neutrino goes only about a meter before it slams into something. They're the only thing that can get any energy out of the interior of that. We also have, nowadays, neutrino detectors, because we've understood, finally, their quantum nature, and we want to investigate that more than anything. So if we get a galactic supernova, and we will, it could be tonight, it could be 10,000 years from now or 1 million years from now with equal probability, we'll have plenty of observables to be able to compare these simulations to.
So if one happens tonight, you got to rush back to Oak Ridge? I mean, what do you...
Yeah, it'll be a big deal. I'm hoping that, so the prime candidate is this star called Betelgeuse, right, which everybody can find in the night sky. It's the big red star at the shoulder of Orion. It could go supernova tonight. It will go supernova, but it could be tonight or a million years from now.
And how are you going to gather your data? Are we all ready for this? We're ready to catch this, right?
We are ready. We have neutrino detectors standing by. In fact, some of the bigger ones will be blinded by neutrinos when Betelgeuse goes off. Wow. It'll be daylight visible for weeks. It'll be brighter than the full moon for months.
So the neutrinos might be predictive then?
They could. They'll be diagnostic of what's going on deep in the heart of the star that we can't see.
So what about, are you applying AI to the mix here at all to help you with this effort?
From soup to nuts. So from not only, for example, doing the kind of ensemble simulations that Juan was referring to, I want to be able to do the whole panoply of progenitor stars, but I can't, right? We, for example, have found that the explosion of a 15.78 solar mass star and the explosion of a 15.79 solar mass star are fundamentally different from one another. But I do want to be able to find places in that space where big changes happen. AI can help me do that. It can help me design the numerical experiments that I want to do. In situ, I also have physics that I can't resolve, some of it being turbulence. In fact, in the compressible hydro limit of what the stellar plasma looks like. So there's another place for AI. And on the end, I want to be able to detect anomalies. I want to be able to pick out interesting things in the flow. I want to be able to pick out interesting things in the energy transfer from that nascent protoneutron star to the outer parts of the star. And a good way to do that is with the aid of AI as well.
Are you bumping up against the limits of computational power and with more kind of seeming to slow down, right? Or getting there?
I've heard every second of my career, which is basically this century so far, that Moore's Law is dead. And it's finally true. And so that's a little sobering. But we still have room to make some progress, I think. We have new modalities like AI, quantum, for example. Now that I know, for example, that these neutrinos that are passing through my hand, their flavor states and their mass states aren't the same. So I know they change flavor. That's a fundamentally quantum problem that I can't do on any classical machine. But we're also making strides in being able to more effectively harness what we have. I mean, the exascale has opened up a lot of room for us. We're now able to do very, very large, fully three-dimensional simulations of big exploding stars. I can, for example, keep track of as many nuclear species as I want. I can tell you exactly what the isotopic composition out of one of my simulations is now. I can literally include every single known isotope and almost do it for free because of GPUs. That's pretty empowering.
All right, Sylvia, is quantum to the rescue for Branson as he runs out of compute?
Yeah, we hope so. We hope to use quantum as the best tool to simulate and better understand those problems that are inherent to quantum, as Branson says. So basically, there are some, nature is inherent quantum. So to better understand nature, we need quantum computers and quantum simulations to run on quantum computers. This is what Feynman said in 1981. And this is what we are looking for, so this quantum advantage. Now, not all problems can be solved more efficiently on quantum computers, but we know that there are some problems that are best described by the laws of quantum mechanics and can be very well described, very well simulated with quantum computers.
So tell me about the interface between quantum and classical computing. I know you're working on that. It's not like, TV killed radio kind of thing, right? We're still going to be using classical computers, even in the quantum world. But tell me how the two will work together.
Yes, correct. So this is what we call hybrid quantum computation. So the idea is that we can subsidize some problems that we know can be solved very efficiently on quantum computers to quantum computers, and then the rest can be done by classical computer, HPC, and so on. So one example can be, for example, molecular structures. We know that the quantum computers can be very good in predicting the energy of those molecules or of particles, or how do the particles interact with each other, and then all the rest can be done on HPC and classical computing.
So as you march toward getting more and more qubits, and maybe someday 1 million qubits, which is kind of hard to imagine. When you see the plumbing on these machines with 12 qubits, it's kind of hard to envision what that's all going to look like. What are the primary technical challenges? Is it in fact just the plumbing, making everything cold enough and quiet enough to make that all work?
Yeah, there are several challenges we are working on, and I'm also an engineer, so I'm very close to the machine and try to solve those challenges. The quantum computers are subject to noise because we want to work at very low energy, which is basically the quanta of energy. So let's say the energy that takes one electron to jump from one orbital to the other. So this is extremely low energy. And so to do so, we have to protect those machines from interacting with the environment. So for superconducting qubits, we put those qubits into dilution refrigerators, so like refrigerator units that go down to 10 millikelvin, which is extremely cold temperature. And still, this is not enough. Still, we observe decoherence, which is basically the time that takes to, you encode any quantum state, and it will decohere to a stable state, which is a ground. And this is what we call decoherence time. So this is one of the challenges, to increase decoherence time, basically to increase the time that we can store a quantum information. The longer coherence time allow you to have longer algorithm, and so this really reflects on the type of computation that we can do. Another challenge is the interconnect. So what we are doing now is basically to create some chips or some units that are really optimized, and those can have hundreds of qubits, for example, and those are really optimized, and we know that they work. And then the idea is we will take a bunch of those and we will interconnect them. However, you don't want the interconnection to be more noisy than the device itself, right? So this is another issue. And then if the interconnection goes for very long distances, then you also have the additional attenuation that is introduced by the traveling of the information for long distances. And then finally, all these introduce errors, and so to really deploy quantum advantage, we need what's called error-corrected algorithm and be able to mitigate those errors. Every time that we try to mitigate the errors with algorithm, we introduce an overhead into the computation. That means that if we have some number of qubits, not all of them are going to be used for the computation, but some of these qubits are going to be used to correct the errors. So yeah, and this is a short list of the technical challenges that we are facing.
So how, I mean, quantum is one of those things that seems like it's always 10 years off. It's a little bit like fusion, but it does, there's been quite a few developments very recently, which give some hope for it. But if you could help us understand, and I know this could be tough sledding being in the quantum world, at least for me, but give us an idea of how quantum can aid in complex simulation processes or field theories for particle physics, for example.
Yeah, as I say, quantum computers are very good in solving some specific problems that involve quantum mechanics. One of these problems is simulating how the fields interact to each other. So if you allow me to sort of step back, explain what is a field, a field is, let's say, an entity or a variable that has a value in any time, in any point of space and time. For example, a magnet. If I have a magnet and I have a piece of metal, the piece of metal is going to interact with the magnet, right? And this is magnetic field. But now in physics, as long as something can be described in the same way, it can be called a field. So one example is a liquid, so water. Water can be described as a field as well. Now, something very cool happened and was discovered by the Nobel laureate Purcell, that the viscosity of the liquids have a certain minimum. So you cannot have any liquid that have lower viscosity than some value. This value depends on the Planck constant. So this means that the liquids that we can also call field are quantized, just like the energy. And so now, if we put together the relativity and the quantum mechanics, we have what we call quantum field theory. Now, why do we care? Because now the universe can also be described as a liquid, basically. And so understanding the viscosity that can be described as quantum mechanics help us understanding the evolution of the universe. So what happened right after the Big Bang and how the universe is evolving. And like this is a very interesting problem, and this is really the quantum computing problem, so the problem that can be simulated very well on a quantum computer.
So there's also more immediate applications like encryption and so forth that,
yes.
that could be substantial, right?
Yes. So as you mentioned, encryption, still leveraging the properties of quantum mechanics, a quantum channel is the most secure channel that we can build. This is because if we are sharing information on a quantum channel, and if there is a spy that wants to enter the channel, it will break the information, which will decay through like a readout process, and basically the information that this bad guy has access to has no meaning. This is a very simplified description of those encoding mechanisms. And so this is why this is one of the applications that can have a high societal impact, for example, for defense or national competitiveness. That is very interesting for both quantum computing and the impact that this can have.
What's it going to take to make a quantum internet?
Okay, yeah, that's that's something that takes maybe more than a decade. So at first, we have to solve the problem of the quantum information, to keep and store the quantum information. And now we have to be able to transport this information for very long distances. Actually, there are good news there, because we know that quantum networks do exist. And it has been demonstrated that we can transport single photon for several miles with very, very low attenuation, also entangled photons. Now the issue is that there is no computing part in that. So we have to introduce the computing. There are several technical challenges also there, really on the physical layers. So how to be able to convert the information from one form of energy to another, which is called transduction. And there are also other type of networking challenges. For example, how do we transport the entangled information? What kind of information we want to transport long distance? What kind of information maybe we can retain locally, and so on.
All right, let's go to our lightning round now. And Branson, for you, we'll give you a buzzer, and every answer has to be a question. Okay.
Got it.
All right, good. So,
I think I remember how to do this.
Let's talk. So, I mean, great excitement about HPC, great excitement about AI. And couple that with the idea that Moore's law might be dead, or is at least in intensive care. I'm curious, Juan, if there is some way to kind of meld all these things together into a hybrid, which takes us into a whole new era of computation. Do you see it that way?
I have to say that we've heard about Moore's law dying for a long time, and as they
You're
say,
skeptical.
the rumors of its death are sometimes greatly exaggerated. I think over time we figured out that with increasing levels of parallelism, more recently with the use of mixed precision arithmetic, with great developments in algorithms, we are continuing to enhance our ability to compute. And I think, as you were mentioning before, over the last 20 years, there's been significant improvement beyond what some of the practitioners like ourselves would have thought would be possible. So I do think we have a number of years still left in continuing to increase the performance of the computations, even if the cost is starting to sort of plateau significantly. Now, I think you were talking about, are there other paradigms that we're going to switch to? And this is something of great interest to me that I've been paying attention over the years. Are there hybrid schemes between a future quantum computing state and, you know, sort of the GPU revolution that we're all riding on over the last few years? I think that there are some solutions where this might make sense, but there are many physical problems where we still have not yet figured out how we're going to do combinations of quantum algorithms and classical algorithms that are actually going to outpace the capability of computing we have today. So as a professor, I would say we really need to look fundamentally at the mixture of these two realms to see where it makes sense in the physical simulation world. So.
All right, if Branson had a buzzer, he would have hit it by now, so go ahead, yeah.
Yeah, I agree wholeheartedly with that. I think my picture of what the first big use of quantum computing is going to be, especially in the context of very high-end HPC, will be a sort of an outrigger to do those problems that are inherently quantum mechanical in and of themselves that are part of perhaps a bigger problem. And I'm actually very optimistic about that. I'll also say something about what Juan said. Algorithms have always won. They always win. They'll continue to rack up wins based on the hardware that smart people are given. And I think we've got some mileage. We just don't get the freebie for every 18 months. We don't get doubling, right? And so in the absence of the freebie, I think the primacy and importance of algorithms may become even more obvious to us.
Chris, to what extent does the cloud make up for more kind of sputtering? If you have so much massively parallel computer capability accessible, do we care as much about more as long as we can pay the power bill?
I mean, yeah, that's been the biggest problem. I mean, cloud isn't actually widely adopted in our world because of the cost. And so the trying to make things more efficient, actually orchestration is where there's been a lot of focus recently, is because things have been honestly ran so inefficiently. And if you, in our world, if you take 100 VFX artists, you have to give them 100 computers. And that's a lot. Well, it turns out at any given time, they're only using about 1% of their power because they're moving stuff around. And so if you can orchestrate that power around, you can actually now make it far more efficient. You might only need 10 computers for those 100 artists because of the way they work. And so if you can identify those patterns, so we're, the issue with that is actually it causes us to be more creative and innovative in how we efficiently utilize them. And so we're now just seeing things come out now where we can do it. We used to have the ability to burst to the cloud, but the costs and power were insanely expensive for what we were doing. So most of our stuff's still on-prem, but it's slowly starting to move this way as we get more efficient.
Sylvia, is there going to be a quantum iPhone?
Quantum iPhone? No, I don't think so. I think the delivery infrastructures that you need are not compatible with, bringing this to our houses. But I have to tell you something. The quantum computers do exist, and we can access to them through the cloud. So this is how quantum computers are available in general to the community, and this is a platform that actually is working pretty well.
So HPC, I gather from all four of your knot holes. See, I can't even count at the HPC thing. From all of your areas, I get the sense that there is, overused word, it would be revolution, but there is significant developments that are occurring right now by harnessing this computer. I assume that's probably not news to anybody in this room, but why don't you just tick through, go ahead, Branson, if you want. What are the things that we are just now learning by harnessing this capacity?
I tell people that I freely admit that I've been surprised by the phase change that exascale computing has brought about. The level of physical fidelity that is able to be brought to bear on a host of problems, all problems. That's the other thing I always like to say. HPC is good for everything, and I think it really has some truth to it. I'm surprised. I've been surprised by how sort of revolutionary really high-end computing and exascale computing has been in the last, say, 18 months, 2 years. We've really made a phase change in the level of detail, the level of physical fidelity, and the sheer number of things that we can do. Some of that's been enabled through cloud resources, on other scales, on big exascale computers like the one that I'm used to. But the sheer ubiquity of computing power that is available, fairly democratically, though we need to work on that to make sure that people can have, more or less good access to computing resources, has brought about really big discontinuous changes in what we've been able to do. And I think there's probably room for more of that to happen as well.
So Juan, would you go along with that? And we're talking about solving some really big problems that it seems we cannot solve otherwise. We've created a lot of complex messes to sort out, including climate change.
Yeah.
And for example, I know you're working on some of the electric aviation ideas that are out there, which are fascinating. Do you have the same sense that things are picking up at rapid pace?
Yeah, I mean, we were talking before this session started. It's a wonderful thing to be in a world where the experts in this domain are actually surprised by the pace of improvement. So I cannot emphasize how much we believe that we've been in a steady progress that was very predictable, and now it's sort of accelerating. So that gives rise to the opportunity to do lots and lots of different things. It's not just about compute, by the way. Lots of compute, hours to minutes or seconds for a single simulation means you're going to want to do lots of simulations at the same time, and you're going to want to store the data. You're going to want to curate it, consume it, have all the metadata, so on and so forth, build models. And I think it's all of that coming together with the help of the cloud. And by the way, I'm an academic, but I spent a bit of time building a small company called Luminary Cloud that it's trying to do all of this in the cloud. That idea of collecting all that data and sort of making good use of it is what gives us the opportunity to solve some of these very hard problems. Why? Because we've been looking at these problems with a microscope in some senses. And I don't mean that in a good way. Instead of seeing the entire picture, we're looking at just specific areas where a human being thinks that an aircraft system, for example, or an eVTOL or an air taxi is going to be working well. But we're now opening up the aperture by looking at the entire design space and trying to figure out what is the right design decision to make, for example. So I don't claim to know much about supernova or global climate, but if you see the publications in the literature on HPC-related activities, you also see that sort of steady improvement in compute performance is now accelerating. And that has also given rise, I imagine, to lots and lots of opportunities to solve the problems, or at least come up with ideas on how to solve these problems.
Chris, are you seeing that kind of quickening pace? And I'm curious if you could have predicted where your business would be right now, even a few years ago.
No, I mean, we're seeing it a lot in the game engine rendering. So, now you can, it's still not quite there, but the real-time rendering is now coming to bear, where instead of using even just CPU power, we've switched largely, not completely, but the programs take a while to switch over to GPU rendering. And so instead of waiting a long time for feedback, you can iterate super fast now. And so even when you're playing a game, some of these latest models I've seen are actually running, like, say, a GAN at the end of the thing on the fly through the cloud, and now you get photoreality out of the game. So we've pushed rendering quite a bit, computationally, and now we're throwing some other stuff on there, and that's where the cloud makes a huge difference, because as you distribute that out, as smart glasses become more of a thing, you're going to distribute out photoreality AR everywhere. That network has to be ran off the cloud no matter what.
So Sylvia, would you agree that this is kind of a golden age almost for HPC?
Yes, I think so. I think the level of scalability that we are facing now, it's incredible. As I mentioned, Feynman said in 1981 that we needed a quantum computer to surpass the classical computers. 40 years have passed. Classical computing through HPC has gone through an enormous growth. This problem is still, this statement is still true for some specific problems where we really need to leverage the quantum mechanics, but in general, the level of modeling and simulations, and you mentioned weather forecasting or imaging that we can do with HPC is really incredible.
So let's talk about some of the logistical challenges. What are the big ones? We talk a lot about the grid and just plugging all these computers into and finding a power source, but there's all kinds of ethical considerations that come up when you have these huge accessible bodies of data and so forth. What do you guys see as the big challenges that need to be overcome now to continue this kind of rapid growth? And anybody can take that. You want to start, Juan?
Yeah, to me, I think the ethics of leveraging this awesome power that we're being afforded are really important in two different areas. I'll throw them out and see what my colleagues here think, but one is the sustainability of the whole enterprise, right? And by that I mean the sort of sustainability of the energy production that is going to go into leveraging the HPC resources and sort of training all the necessary models in order to make progress. The second one comes a little bit more from an educator point of view. It's sort of the ability for everybody to have access to these types of capabilities. I think right now it's only a few privileged ones, even in the US, who have access to these types of things. It has to be much more pervasive and it has to impact society widely. I do think that we need significant programs in order to have that accessibility of not just the compute capability, but also the model training and inference.
So haves and have-nots, that's always a concern.
Yeah.
Chris, you want to weigh in on that one?
Yeah, I mean, I think it's, I've become obsessed with efficiency lately, in that it's an architecture problem. And even recently this week, a new paper came out. You know, and the LLMs can only scale so far. You know, they're just wasting. You see the real innovations coming out of these small places in China or France that have nowhere near the resources, but come up with a model that's almost as good as GPT-4, if not better in some ways, with way less resources. So I think, you know, because it was the beginning in a sense, a lot of it was brute forced. And I think it's actually caused a lot of the issues of noise and, you know, hallucinations or whatever. But I actually think you know, the compute power is fine, and people do need access to it, and they should, you know, almost make some of it a utility in some sense. That it actually does breed a lot of innovation not to have access to that.
Well, Branson, yeah, I mean, it's kind of like fatware, isn't it? But I mean, if there is, you know, most new products are big and clunky initially, right? Is that what we're seeing here, or not?
I'm not sure they're big and clunky, but you know, we talked a little bit about how, well, I said, I think, that algorithms always win. Well, you know, you started the question talking about data per se. I would claim that perhaps when it comes to data, curation always wins. And I think that's the next big sort of discontinuous jump that we're going to have to make if we want to, for example, train bigger and bigger models. I'm always struck that our colleagues who are doing very, very cutting-edge AI, it always seems to me that they're sort of rediscovering things that maybe the HPC world has known for a long time. But they explore it. They're exploring it way faster than we did. That's one thing, because the resources are so vast. But I think that it's also becoming clear to them and clear to us that data curation and the quality of data that go into big models is an important thing. And that actually has its roots and has direct ramifications and causes and effects also rooted in this sort of democratization access that we've been talking about. Because good quality curation requires a fulsome look at the origins, the provenance, and all the other sort of things around data, everything about the metadata, if you will.
So how do you see AI enhancing the HPC landscape then?
Like I said, you know, at the leadership computing facilities, we see that AI is not a big deal because it's everything we do. It's infused into every single project that we have. It's infused in what we do day to day. It's just a standard operating procedure at this point, and that's an unusual thing when it comes to science, period, and in computational science even, which has been, you know, as we've discussed, galloping along for several decades now. The gallop has certainly accelerated.
Sylvia, what do you see as the big challenges?
Yeah, I think the big challenge, I have to echo what my colleagues say, is really accessibility. So we need more developers, at least in the field of quantum computing where I am in. I think we need more people being able to access testbed facilities, quantum computers, as this is the best way really to make progress. National laboratories, I think we can leverage infrastructures at national laboratories and also go hand in hand with academia and the industry in order to be able to give more accessibility and basically educate and form more developers.
Yeah, this is not going to continue without an educated, motivated workforce of engineers. Juan, I know you've thought a lot about this. Tell us your thoughts.
Could I sort of interject
Yeah.
for 1 second about sort of the physics-based AI world?
Yeah.
I do think that we're at a point where, you know, LLMs have been trained with every single document available on the web. The next frontier is to create large databases of physical simulation data that can actually be trained can be used to train these models to be enhanced with an understanding of the physical world. And I think that's a massive undertaking. And I'm not quite sure what the answer is. I sure hope that some of the young people in the
There's
audience.
a lot of world models being trained right now, and I was amazed at how well an LLM, without having any access to spatial data, was able to recreate three-dimensional scenes. And then when you give it a little bit of information on multimodal, it's incredible how well it does. And that's to be the next big training scale up, is all the world data that you're going to gather from, you know, every sense, from audio to video. And so far an LLM is, I mean, for lack of a better analogy, it's like the Helen Keller. It has one sense. And now if you give it all these other senses, it's incredible the understanding that it's going to gain about things.
And what comes out it is not uncanny valley stuff with, you know, 6 fingers, that kind of thing?
The AI videos now, I mean, temporal coherency is essentially solved. And, you know, even last night, you know, a new open source model just dropped that I tried out, and I'm like, pretty good, you know, and that's, you know, there's now startups, which is why they try to sign you up for annual plans, because within 3 days they'll be obsolete. So it's like, you know, so basically, but it's like, it's happening so rapidly now that you can't even keep up with it.
You really are the GitHub king, aren't you?
I've started like 800 repositories of everything.
I think for discovery science, though, I think it's a big open question about what we can learn and what we can understand from such models. I think that's my main question. What can models, physically motivated, trained models, multi-sensory, what can they do to aid my understanding of what's actually going on? And I think that's a little bit of an open question.
And I have to say, you know, how can you make sure that the predictions of these models actually have some error bars attached to them, so you can understand whether the physical phenomena that you're observing is actually real or not?
We're not doing science unless we have error bars.
Right.
Period.
Little hallucination won't hurt us every now and then, I guess. So let's talk about how we can encourage young people to pursue these kinds of fields. Sylvia, is quantum itself attracting the best and the brightest now?
Yes.
And you know, it's an important question for the United States, too, to keep and retain smart minds to do this.
Yes, we see a lot of interest from young people around quantum computing, in general, maybe emerging technology. Probably my colleagues can say the same around artificial intelligence, machine learning, and so on. And there is also quantum machine learning. So all these fields is attracting a lot of people. Every time we open an application for any kind of opportunity, we receive an overwhelming amount of applications, so which is really great. So we see a lot of interest. There are some challenges that we face, and we are a national lab, so we mostly work on the technology and the algorithm, but there is also a component of education. So as a sort of educators, we are also trying to understand what is the best way to form this smart quantum computing workforce. It is an extremely multidisciplinary, cross-functional field. You know, people that works in the algorithm. We don't have yet a hardware agnostic algorithm. So the idea is that even people that just work on the software need to have some understanding of the hardware platform that they want to program. And so it's a real challenge to understand how to form, you know, the next workforce.
Branson, you seeing bright young minds that are engaged in this field, and enough of them?
I think so. I mean, enough of them. That's a good question. But I think the excitement around, again, when I was young people's ages, you know, way back in the Stone Age, I was absolutely enthralled with the notion of being able to bend a computer to my will. That's the thing that really hooked me. And I think that my experience with students across the sort of ages has been, if you can get them doing that, realizing that they can tell the computer what to do and then let it go and let it tell them something back. It's incredibly empowering, and it's something new in the human experience just in our lifetimes. That excitement, I think, extends all the way from understanding the hardware, understanding the software that they're using, and its interplay to actually get understanding. And so I think all we have to do is hook them. Getting people exposure to being able to do that is perhaps the hardest thing.
Juan, would you agree, that kind of hands-on approach?
Yeah, I was going to say I can comment on college level education, but I think in order to attract the workforce of the future that's going to do the amazing things that have been done until now and further, we start in K through 12. And I'll say something that's going to get me in trouble with this audience. With that audience, those folks or those students, it's not really only about the software, it's about the combination of the software and the hardware. Mm-hmm. So I love the robotics competitions that people do, because we're here to excite young minds to actually pursue careers in science and engineering, et cetera, et cetera. And for God's sake, let them build a rocket and launch it and do some analysis.
It's very visceral, yeah, it's very visceral.
Yeah. At the college level, undergraduate and graduate, then I think you can open up the doors for, the amazement of solving a partial differential equation that actually resembles the physical world and actually tells you something you didn't know about the physics of a particular problem. That is very, very exciting.
So to solve, is there a problem here? Do you feel like there's not enough people gravitating toward this field?
So we've leveraged levels of abstraction amazingly well, particularly in machine learning. So, Python-based, everybody can actually do something that is amazing, large computational tasks, no detailed knowledge required of the underlying technology that is enabling all of that. But I think as we move forward with the problems that remain, we're going to have to be training the people who are enabling all of that for everybody else. And again, I'll say something that gets me in trouble with my academic colleagues all the time. Our education for that type of person is highly siloed.
So you want to start at third grade?
Second?
Starting at third grade is where we need to be.
Starting third grade, motivating people, but I think...
So that's a big problem.
Yeah, it is. It is a huge problem. I think we need big ideas in this country and around the world in order to make sure that, we train the workforce of the future and we actually get them hooked on the fact that these are great jobs, intellectual stimulating with big societal impact as early as possible. Otherwise, we've lost them by the time they get to sixth grade. So.
Sylvia.
I just want to say that I think it's a greater problem to stimulate a student in K-12 than in third grade. My kids are in second grade, and they are really interested into science, and they ask a lot of questions. And this is probably something we don't have from grade 12. So,
surely they know about entanglement in your house, right?
Surely, but I think this is something that we can probably give more access. So give more access to facilities and to test beds, and also just to ask scientists session or engineers session to give them the chance to be curious.
They need to see scientists as heroes, that kind of thing. That would help too. Chris, what are your thoughts on education and ensuring that there is a strong and smart workforce, not just in your part of the business, but for HPC writ large?
Oh no, I'm with Juan. And my dad was the commissioner of education for the state of Alaska, so it's a lot of opinions, and our system's still built around training light manufacturing workers, and that's what's encouraged. So it's a lowest common denominator, and so the reward for that sort of thing isn't, it's not as encouraged, and there's a lot of resistance by the teachers and the system. They're like, oh, that's cheating. But when Bronson says he wanted to bend a computer to his will, what I hear is someone had an imagination, and they were picturing something, and so that should be rewarded. And that's where generally a lot of good science comes from. And so as we try to figure out how to interact with these things on an educational level, because if you can just use them and pass the test, the thing is there's still a million ways to test for critical thinking, and it's how you use it. And what are you actually demonstrating? Because, just checking a box on a test is not really demonstrative of any kind of understanding. And we've all known that for a long time. But I think now this might actually force the issue. And so I think obviously we can't just treat, you know, haves and have-nots. We have to pluck. You know, my hope is that it democratizes, because the smartest person ever will probably never know, because they were too busy trying to feed themselves to invent, you know, do what Sylvia's doing. So my hope is with the accessibility and education, people can see what's possible. Because for me, I found that a lot of these tools have just widely opened up my imagination.
Right. So let's close by getting out the crystal ball here a little bit. And whether it's in your field or HPC in general, I'm curious, what big problems do you see it solving, or do you hope it to solve in the near to medium term future? You want to start with that one? What are the big ones on your plate, or that you hope that this capacity can deliver for us on some of these big problems we face?
So not my direct field, but uses the same physics that I use. I think the climate emergency and the acceleration of the technological solutions, policy as well, and economics, of course, but the technology solutions that are going to enable us to create fuels from CO2 in the atmosphere in a sustainable way, to make sure that we maintain emission levels at real levels, to make sure we have space observations that can actually monitor the Earth and actually tell us where the hotspots are and the problems are. I think that's going to be the big thing for the next 20 years.
And it's hard to think of a bigger problem than that one, right? That's as good as it gets. Chris, what do you think about big problems in HPC?
I think, well, it's what you started off with. I think once the simulators and the architecture are in place, you will need a ton of HPC to basically run a ton of genetic simulations. And you basically let the systems go find their own problems. You know, the same way they found that, you know, auto-tuning their own hyperparameters is way better than anything we come up with. You allow them basically to simulate these things, you know, whether the goal seeking is to solve the climate or come up with a new economic model or maximize the survivability of the most amount of people in a certain time series. You just let it go off, and that it'll be a ton of compute needed because of the general inefficiencies there.
And you let it go off, do we worry about that, or is it okay?
I mean, we've remade Terminator 10 times. So maybe we'll come up with a new script for once, but
it's your business.
There's going to be a lot of worry. I mean, autonomous drones are a worry. You know, the military aspect of it's a massive worry. But you know, yeah, there's a lot to worry about.
Well, it's easy to go down the dark road, and certainly Hollywood has helped us do that. But it seems to me our problems are so complex that we have to embrace it at some level.
Well, no, eventually they beat. You know, in Star Trek, Data had an evil brother, and eventually they beat him. So.
Just you got to play the long game. Branson, go ahead. Your thoughts on this?
So I think you just said it, Miles. Complexity. I love. It's one of my favorite sayings that there's no one killer app for HPC or very, very high-end computing. It's Catholic purview is the thing that really attracts it. It makes it most attractive to me. But the management of complexity, allowing humans to be able to reason about incredibly complex problems, from climate change to trying to blow up a star to get enough iron-60 out so that I can form a solar system. Sort of from one end to the other, it's the management of complexity that I think HPC really allows us to do. With all these new modalities, including things like AI and quantum, all that does is it adds to our ability to manage that complexity and to think, maybe augmented directly or indirectly, by HPC, but HPC makes managing complexity possible in order to gain new information and new knowledge.
That is a simple and I think objectively true statement, but people get worried about all this. Why do they get so fearful?
I think people get worried because they want to be able to justify in a very simple, visceral sort of value proposition why we should continue to do. Why we should continue to invest, why we should continue to train people. And the answer is, yeah, the simple, straightforward thing is stuff's not getting any easier. It's only getting more complex. And because of that, since this is the only way forward, you better plow a very, very wide road to be able to get there.
And make sure there are guardrails on it. And that's the tricky part, right?
It could be, but I think people think about that as we move into an age where data is sort of gaining in primacy. I think that's coming to the fore. I suspect we'll have some growing pains between now and the time of having a more or less reasonable regime to make sure that those guardrails are high enough. But that sort of churn is where innovation happens as well.
All right, Sylvia, you get the last word on what the big challenges that this world can meet and conquer in the coming years.
So from a scientific point of view, I would say, as I started, the viscosity of the universe. As an engineer, I say this because the technology advancement that we need to do to arrive to this result and to solve this problem is, is a great leap, and so it will have also great impact in general in the society, from the workforce point of view to predictive models, for example, for weather forecasting, and also developing models that go hand in hand between quantum computing and the HPC.
All right, that's the final word. Sylvia, Branson, Chris, Juan, thank you so much for a very stimulating beginning to this SC24 conference. Please give them all a round of applause. So obviously we're just getting started with this record-setting conference. For now, we'd like you to all go to Exhibit Hall, the gala opening in Exhibit Hall B. There'll be a ribbon cutting, and we look forward to seeing you there. Thank you for joining us.